Morning, all of you. In today's session, we are going to start with the engineering chemistry, polymeric materials. Okay, so in addition to this, we already completed CSR, NATE, GRF, chemical sciences, entire detailed explanation of solved question papers since 2014 to 2020. All these available on the channel called World of Competitive Chemistry. So we already completed entire 10th class chemistry and physics. So that topic also detailed explanation available on the channel called World of Competitive Chemistry. And we completed engineering chemistry topics like water treatment and also molecular structure and theories of bonding, electrochemistry and corrosion, stereochemistry, how the dimensional arrangement of molecules will be there and what could be the reaction mechanism in the organic chemistry. And also we completed spectroscopy, advanced spectral techniques in order to interpret the unknown compounds. All these topics were completed, all are available in the channel called World of Competitive Chemistry. Now we are going to discuss about polymeric materials. So just to let us see simplest description about the polymer. So as we are aware that polymeric materials are very well known, and we are most familiar with the compounds which are extracted from these polymers. Nowadays, our lifestyle is mostly associated with these polymeric materials, and even in the environmental perspective, nowadays so many type of biodegradable polymers are available, and they are finding the most therapeutic as well as daily life applications. So let us discuss about the introduction for this polymeric materials in today's session. So today's topics are about what is polymer. We are going to introduce what is polymer here, and the classification, extensive classification for these polymers are going to be described. And in the next session, we will go with the types of polymerization, degree of polymerization. These topics will be covered. But in the today's session, just we are going to take the introduction. This will be the part one, where what is polymer and how it is extracted, how it is synthesized from taking monomer as a starting material, what kind of classifications are available, and what kind of arrangement of polymer is possible. All these topics are going to be discussed in detail. Let us see. Polymer will be started with the starting material called a monomer. Monomer is defined as any material or molecule which can be converted into a polymer by combining other molecules in the same or different type. Mono indicates what? A single unit, which is a starting or fundamental unit, so which in turn get combined in such a way that used to give the larger one. Let us assume monomer will be a single brick. These bricks will be arranged in a sequential manner in the one particular order, so that a big building construction is possible. In this way, we can say monomer is the starting one. This is a confined unit which can be arranged in the sequential manner in order to construct the complex polymer. That kind of a fundamental unit is designated as a monomer. Then what is polymer? Polymer is derived from the classical Greek. Poly means many and mer means repeating parts or repeating units. Right. So here, such as kind of single monomeric units when combined, so that here polymeric formation is possible. If monomer was taken as a single unit, if two monomers get combined, is called a dimer. Dimer, if when added with any other monomer, called a trimer. 3 units will be there. Oligomer means some of the monomers, a little number of monomers when combined. You may say 10 units, you may say 20 units. In this little number of monomers when combined, so that here oligomer formation is possible. Oligomer stands for what? A combination of monomers in the little number, small number. Poly means many. This will be the complex one. Lot many such monomers get combined, so that we will get a high molecular weight, a huge molecule denoted as a polymer. So in this manner, so polymer and monomer are introduced, and polymer chemistry plays a vital role in our daily life, not only for the domestic application, but also for industrial applications in automobiles and aviation. Different kind of means of transportation. In all the fields, we are applying polymers in a substantial way. That's why polymer plays a vital role. Now let us see the introduction for these polymers. Polymers are the macromolecules. This is in either synonym for the polymer. Macro means what? It's a huge or the large molecule, right? So this macromolecule formed by linking together of large number of smaller units called monomers. Monomers are interlinked in such a way so that your macromolecule formation is possible, in turn called a polymer. Polymers are the joint molecules. They are formed by the joining of monomers. We can say it is a joint molecule, and it is composed of high molecular weight. Because, for example, monomer is of 10 molecular mass. 10 molecular mass will be there. If this 10 molecular mass is combined in such a manner, these many atoms, these many monomers got combined, what happens? It obviously will retain the higher molecular weight. That's the reason why polymer will retain the higher molecular mass. For example, monomer of ethylene, it is the simplest polymer of polymeric chemistry, where ethylene unit is the simplest one, simplest monomer. It is composed of 2 carbons joined by the double bond, and this ethene molecule number of, for example, you are going to combine 100 ethylene units, so that here polythene got generated of repeated combination of these many 100. N denotes 100 over here. That means how many number of units are going to combine, that will be denoted with the N. Right. So here ethene atoms, ethene monomers get combined by the process called polymerization. And here the formation of huge molecule of 100 monomers combined in a sequential manner, and we will get a linear polythene molecule, which is denoted as a polymer. This is the simplest polymer you can achieve by taking ethylene as a monomeric unit and linked with many other ethylene units to form the polythene. A large number of vinyl chloride, for example, vinyl chloride, how can we get? When these hydrogen, one of the hydrogen replaced with chlorine, that will be designated as a vinyl chloride. And here the polymer generated will contain one of the hydrogen replaced with chlorine. The remaining structure resembles with this polythene exactly. That is called a vinyl chloride, PVC. Vinyl chloride is a monomer, and the subsequent polymer formed is called polyvinyl chloride. That will be the final product we will achieve by the process called polymerization. The single repeating unit used in this polymerization process is designated as a monomer, and the resultant high molecular weight final product is called a polymer. Here the polymer formation is possible by the repeated combination of monomeric units. You can find the application for this polythene. So here plastic tins, plastic containers, plastic food material containers are available, and even polythene furniture is also available in so many fields. Polythene packaging wrappers are there, and that used for packaging purpose as well. In this manner, so many applications you can find with this polythene. Now, let us see a detailed classification about polymers based on the backbone. So polymers can be classified into basically two kinds. One is based on the backbone, based on the origin. So based on the origin, in the sense, if we are extracting polymer in the laboratory, or else a polymer directly taken from the nature. So on the starting point from which you are extracting the polymers, these are classified into 2 types. One is called a synthetic polymer. Second is called a natural polymer. Natural polymer is nothing but which occurs in the nature. So if we want to define these natural polymers, human being is regarded as a natural polymer. How can we say? Because our entire body is composed of cells. These cells are combined in a repeating manner, so that here human being is a big polymer composed by the natural cells as a repeating unit. These are designated as a monomers, right? So in this manner, natural polymers will be there. Again, natural polymers, polysaccharides and protein based. Polysaccharides are nothing but energy based polymers, and protein based polymers also present. So polysaccharides give the energy to the living organisms. Proteins are the growth factors for living organisms, right? So here polysaccharides are nothing but glucose, fructose, starch, sucrose. All these are the part of polysaccharides, and these are the energy contributors, where these polysaccharides again of the various kinds. For example, cytosine, and hyaluronic acid, agarose, and cytodextrin. Dextrin is nothing but glucose itself, dextrol. All these are the part of polysaccharides. A simplest example is cellulose as well. That is available in the plant material, which can't be digested in the human digestive system. That is also polymer of n number of repeated units of glucose units, so that here it is also considered as a polysaccharide. Now let us see what are the examples for protein-based polymers. Gelatin, it is a gum type of material, gel type of material. Albumin, this is also a protein material. Collagen, collagen is present in our bone system, so that is also a polymeric material. Elastin, so having the property of elasticity. So all these are the materials of polymers. These are having natural origin. So these are the part of natural polymers based on the origin. Now let us move on to synthetic polymers. Synthetic polymers are nothing but which are prepared, which are synthesized in the laboratory. These are further categorized into biodegradable, non-biodegradable. Biodegradable polymers are nothing but which can be decomposed by the natural means of decomposition by the microorganisms. Let us say that may be a bacteria, that may be a fungus, that may be a protozoan, which available, which is present infinitesimal size. They secrete the enzymes and they would like to decompose the system, whichever present as a waste, garbage present on the earth. So they secrete the enzymes, and degradation of these materials are possible so that they will be recycled further. These are called a biodegradable polymers, and some kinds are present which are non-biodegradable. Nowadays, we have most concerned about the biodegradable polymers with respect to the waste management, solid waste management, and the recycling process. That's the reason why biodegradable polymers plays a vital role in the polymer chemistry. Now let us go with the further classification of biodegradable polymers. Phosphorine-based polyanhydrides and polyesters, polyamides, others. When such kind of polar functional groups are present like amide, ester, and anhydrides, so when such a kind of functional groups are available, what happens? They get decomposed easily by the action of enzymes secreted by the microorganisms. So let us go with the phosphorine based. So phosphorine based biodegradable polymers are polyphosphorate, polyphosphozines, polyphosphoranes. So all these are the part of biodegradable phosphorine based polymers, which are synthesized in the laboratory, because these are the part of synthetic polymers, and another is polyanhydrides. So here polysebacic acid, polyadipic acid, polyterephthalic acid, all these are the part. So these are the kind of dicarboxylic acid systems. When dicarboxylic acids get combined, what happens? They get dehydrated so that anhydride formation is possible. So such kind of anhydrates are regarded as a biodegradable, being these are polar in nature. And in case of polyesters, ester linkage is nothing but O-C double bond O group when connected in between two carbon chains. Those are regarded as a polyester. R-C double bond O-R is the ester moiety, which is biodegradable by microorganisms. Let us see what kind of examples are laying under this category. Polylactic acid, this is a vital compound in the medicinal chemistry, because lactic acid sutures are available which are dissolvable, need not to remove further. Once this kind of sutures used in the post-surgery stitching purpose, it is not required to remove these, because these are dissolvable, they get mingled or mixed with the human body. And neither is about polyglycolic acid, PGA. Polyglycolic acid is also neither biodegradable and find substantial applications in the medicinal chemistry. These materials can be blended further. Polylactic acid, polyglycolic acid can be blended further in order to improve the strength, and they will give the artificial strength. Artificial bone fixation is possible by means of these blended materials. And even heart diseases, those who are suffering with the heart blockages, blood clots are there. In that case, artificial stents also made up of these polylactic acid and polyglycolic acid as well. Polydienones, polycaprolactam. Caprolactam is the material used for the synthesis of nylon, right? Nylon threads are there. And these are also polycaprolactam. Being caprolactam is a cyclic compound. So where cyclic ester is there, that will be further involved in the polymerization, will give nylon 6 polymer, which is biodegradable in nature. Polyhydroxybutyrate. Polyhydroxybutyrate is also another kind of ester compound which is biodegradable in nature. So here this is also most important material in the polymeric compound, having wide range of applications. Polydioxanones and polydiamines, polymalic acid, polyhydroxyl butyrate. All these are the kind of system. How the ester get generated? One of the monomer should contain hydroxy active terminal functional group. In either growing chain or in either monomeric chain should contain carboxylic acid and the terminal center. When hydroxy and carboxylic acid get condensed, condensation get carried by the elimination of water molecule, substantial formation of ester is possible. These are biodegradable in nature, so that recycling of materials are possible. They will directly mixed with the earth, and there is no solid deposition in the earth crust. So this is the most advantageous kind of material. Another is called polyamide. What is the origin for the polyamide synthesis? In order to synthesize the amide, the monomer, one of the monomer should be NH2 group containing a growing chain. In either one should be carboxylic acid. Hydroxycarboxylic acid will give the ester NH2 and COOH. That means amine and carboxylic acid upon condensation will generate amide as a polymeric substance, which is a biodegradable in nature. Example pertaining under this polyamide will be polyaminocarbonates, polyaminocarbazide. So these are the class of biodegradable polyamides. Amide functional group is NHC double bond O group will be there. That is called amide functional group, which is generated by condensation of NH2 with the carboxylic acid, right? So other kind of substances are polycyanoacrylate, polyurethanes. So all these are the materials are the class of biodegradable and which are synthesized in the laboratory. Now let us go with non-biodegradable. Though these materials having wide applications but not decomposed by the microorganism action. So even microorganism action is not there. It is possible to recycle them. Under different conditions we can recycle. This is if it is properly treated, it is also not causing any kind of environmental impact. Proper treatment is required for them, right? Let us go with these non-biodegradable materials. The kind will be acrylic polymers, and these are the cellulose derivatives. Acrylic polymers are nothing but a polymethacrylate. So acrylic acid is nothing but when we are having the functional group. So acrylic acid is nothing but carbon-carbon double bond containing groups will be there. So in that kind of monomers when condensed, so that here polymethacrylates will be generated. Polymethyl methacrylate. Polymethyl methacrylate in the sense any other methyl side chain will be there. And polyhydroethyl methacrylates. Here the methacrylate is the major functional group which is used in the polymeric materials, and these are non-biodegradable. Another is about silicones. Silicones are nothing but the materials which composed by silicon and organic moiety with oxygen. Those are called silicones, and siloxanes will be there. Polydimethyl siloxanes. Here, these polymers will be composed of silicon, and side chain alkyl groups will be there in addition to the oxygen. So this kind of long chains are regarded as the silicones. Colloidal silica will be there. So colloidal silica is nothing but silica denotes what? SiO2. SiO2 is the repeating unit of silica, where sand is the simplest example under this category. Colloidal silica is also non-biodegradable, but higher strength will be present for these kind of polymeric substances. In either class of non-biodegradable will be cellulose derivatives. Though cellulose is a natural origin material and it will be the part of these natural polymers, but some of the semi-synthetic and purely synthetic materials will be originated from this as well. Cellulose acetate in the sense here blend cellulose will be the natural origin, and remaining another structural modifications will be there, so that here we can say it is the kind of semi-synthetic origin. Carboxy, methyl cellulose, ethyl cellulose, all these are the part of cellulose based. Cellulose is the purely material of polymer of glucose. Repeating units of glucose will be there, and some other structural modifications, so that it will be regarded as a synthetic polymer. Another will be called other kind of non-biodegradable will be ethyl vinyl acetate, hexamers and polyamines, polyvinyl pyrrolidones. All these are the class of non-biodegradable. Now let us go with any other type of classification. So till now we discussed with one branch of polymeric classification, that is based on origin. So whether they are natural or artificial made in the laboratory. So based on this classification, two kinds will be there. One is natural, second is synthetic. Now we are discussing about the classification purely based on whether it is purely composed of carbon or other than carbon. Based on that also classification will be made. Polymer, which is made up of carbon chain as a backbone. So here long chains of polymers which are composed by the carbon backbone is one category. Other than carbon also incorporated, that is another category. So in this type of classification will be there under this polymer categorization. Polyvinyl chloride is the simplest example of carbon chain backbone. PVC, that is most familiar term we can hear, because PVC pipes will be there for irrigation purpose, and PVC furniture will be there. PVC used as a electrical insulator as well. So many fields PVC find applications. It is the well known plastic for us. Another is about polythene. Just now we discussed about polythene. Polythene is made up of ethylene units got repeatedly combined, and it is purely of the carbon backbone chain, and it is a linear polymer without any side branches. It is the simplest polymer generated and find the wide range of applications. Based on the density, polythene is of two kinds. One is a low density polythene, high density polythene. Low density polythene used as a packaging covers. High density polythene somewhat tough material which used in the manufacturing of utensils of household and even other materials of somewhat strong. So another is about polyvinyl alcohol. Polyvinyl alcohol is nothing but where we are having carbon-carbon double bond and a side chain hydroxy group will be there. These will be repeatedly combined, is a part of carbon backbone containing polyvinyl alcohol. It is also part of carbon chain. Polyvinyl pyrrolidone. Polyvinyl pyrrolidone means a pyrrolidine. Pyrrole is the 5-membered ring system. So here vinyl group will be there, so that it is also the part of this kind of category. Polyvinyl acetate. Polyvinyl acetate in the sense acetate group is nothing but CH3C double bond O group is called the acetate group, and the vinyl is nothing but carbon-carbon double bond, so that it is the carbon chain, carbon backbone polymer. Polypropylene. Polypropylene is nothing but 3 carbons chain that will be repeated several times. So propene is nothing but 1 carbon-carbon double bond and 3 carbon chain will be there. That is the part of this polypropylene. And second category, so here carbon backbone compounds of these and any other than carbon also present, amylose. Amylose is the part of non-carbon backbone containing material. Polyglucoside alpha 1,4 is the compound which is composed of heteroatom. What is the heteroatom laying in this compound? Oxygen is the heteroatom. Another heteroatom backbone chain will be polypropylene oxide. Again, here the heteroatom will be oxygen. Polyethylene oxide. Along with the carbon, other heteroatoms also laying, also composed in the backbone of the polymeric chain. So in all these cases, oxygen is the heteroatom you can find. Pectinic acid. Here also acid is composed by oxygen, so that all these are the compounds, polymers, which are pertaining oxygen as the heteroatom. In this manner, you can classify the organic compounds based on their origin and even based on the carbon backbone, and even so many other type of classifications are also available. And now we are going to discuss about another topic called tacticity. Based on the synthesis, so long chain carbon will retain if side branches are present in the compound. These side branches arrangement will be in different forms. That based on the arrangement of side chains in the longer polymer, they are categorized into isotactic, syndiotactic, and atactic. Okay, so here the condition, tacticity is nothing but, tacticity denotes what? Arrangement of the side chain branches and the long chain polymer is designated as a tacticity. So that arrangement may be three kinds. One is called isotactic arrangement, second is called syndiotactic arrangement, third is called atactic arrangement. What is meant by isotactic arrangement? Isotactic arrangement is nothing but if side chain, I'm indicating as a R group. R denotes what? Any alkyl group will be there. That may be ethyl, methyl, propyl, whatever the side chain. You may take even benzene as well, right? So any side chain may be taken. In case of iso denotes what? Same. Means all the side chains are laying on the same side. So either bottom side or top side, but all are in the uniform arrangement, that will be on the same side. If you observe this, the long chain polymer, all the R groups are denoted with the wedge bonds only, thick bonds only. That indicates what? All these alkyl groups are laying towards the VR. Means all are on the same side. Iso means the same side. That's why isotactic denotes what? All the side branches are on the same side. All asymmetric carbons have the same configuration. Methylene hydrogens are meso and forms helix of minimizes substance interaction. This is regarded as the isotactic arrangement. Now let us see syndiotactic. Syndiotactic denotes what? Alternate arrangement will be there. One of the alkyl is positioned towards the VR. Another alkyl completely away from the VR. For example, this alkyl group is towards the top side, and immediate in either side chain will be exactly opposite, back side. Front, back, alternate arrangement will be there. One is towards the VR, another is away from the VR. One is wedge bond, another is dotted bond will be there. So in this manner, syndiotactic denotes alternative arrangement will be there. One is above, one is below, above, below, above, below. In this manner, they are arranged. Let us see. Asymmetric carbons have the alternative configuration. Methylene hydrogens are racemic in nature. Racemic in the sense, some part will be in the towards direction or right hand side direction. Some other part will be in the left hand side direction. That's the reason why it will become 50%, 50%. So this will be a racemic one. Polymer stays a planar zigzag conformation. So here planarity will be there and a zigzag random arrangement will be there. That is denoted as a syndiotactic. Syndiotactic denotes what? Alternate arrangement of the side branches on the growing polymeric chain. And next is about atactic. A means what? No. Means there is a randomness. So here tacticity will not be obeyed. That will be very random in nature. Zigzag manner will be there. So here one alkyl group is towards the VR, another alkyl away from the VR, another towards the VR. Here see, there is no repetition of the properties. Here 2 are towards the VR only, 2 are away from the VR. That means there is no sequential arrangement. That is denoted as atactic. Asymmetric carbon have the statistical variation of the configuration. We can't define, we can't find the regularity in their arrangement. That is denoted as the atactic arrangement. Purely tacticity based on the arrangement of the side chains. Either all the side chains are in the same side or different sides. Based on the tacticity can be categorized. So here tacticity will be basically 3 types. Isotactic means only one side. Syndiotactic means alternatively arranged. Atactic means randomly arranged. This will be the tacticity of the given polymeric chain. By this we completed today's session. In today's session, what we discussed, let us recall what is monomer, what is polymer, how can we categorize, how can we classify these polymers, and what is the tacticity involved in the polymeric chain formation. So hope this session will be helpful for your preparation. Thank you very much for your consistent listening. Thank you one and all.